All right, guys, let's look at the next section, 1.5, which is about substitution method for solving differential equations. So in some ODEs, we can use a substitution method to convert them into one of the types studied before, such as separable, linear first order, etc. We already have learned how to solve certain types of equations. Some equations are not exactly of those forms, but if we make a substitution, proper substitution, then we can convert them into those types. Now, what would be the substitution? Well, that depends on the example, and that depends on the type of ODE that is given to us. Let me show you in a few examples how you can choose a proper substitution. For example, let's say solve y prime equals x minus y plus 1, the whole to power 2. Well, this is right now, it's not separable and it's not linear first order. But if you make a substitution, you can probably guess the substitution. If I call this expression on the right-hand side, x minus y plus 1, I call it, for example, u or v. Then right-hand side becomes v squared. And what would be the left-hand side? So let's look at the situation. So let's say, let v equals x minus y plus 1. Then dv to dx will be v prime. Derivative of this function here will be 1. Derivative of x is 1 minus y prime plus 0. Derivative of 1 is 0, which is 1 minus y prime. So that means y prime will be 1 minus v prime. Then we will have 1 minus v prime equals v squared. Or I can write it as v prime equals 1 minus v squared. See, this is now separable. Originally, it was not separable, but now it's separable. I have all v's on one side and all x's on the other side. So if I write this one as, now we can, now we have a separable equation. So we have dv to dx equals 1 minus v squared. Now we can divide both sides by 1 minus v squared as long as 1 minus v squared is non-zero. So this is the idea that we use for separable equation. You have to divide by what we call the g of y. In this case, it's v. As long as it's non-zero, 1 minus v squared, if it's non-zero, we can divide by it. So again, we can consider two cases. Case 1, if v is equal to 1 or v equals minus 1 as constant function, as a constant function, then v prime will be 0, which is same as 1 minus v squared. And so that means we have solutions. So v equals 1 and v equals -1 are both solutions. Maybe I can write it this way. We have, so that means both v equals 1 and v equals -1 are solutions for our ODE. But remember, our goal was to find y. See, when you read the question, there is no v. It's y. You want to find y. The goal is to find y. V was the substitution that we introduced later in order to solve the equation. But still our goal, our final goal is still to find y, not v. So once we find v, then we need to find y. These solutions will lead to the following solutions for y. Please remember the relation between v and y. The relation is here. So these solutions will lead to the following solutions for y. So we know that v is x minus y plus 1. So if v is 1, then you will have 1 equals x minus y plus 1. That gives me y equals x. And if v is -1, then you'll have -1 equals x minus y plus 1. That gives me y equals x plus 2. So I already found two solutions for my ODE, which two solutions for y equals x and y equals x plus 2, corresponding to v equals 1 and v equals -1. And these are the solutions for case 1. Now for case 2, if v is not 1, not constant function 1, and v is not constant function -1, then in that case, of course, 1 minus v squared will be non-zero. And then we will have dv over 1 minus v squared equals dx. Remember, we had our equation was dv to dx equals 1 minus v squared. So dv over 1 minus v squared equals dx. And then this means dv, I can use the partial fractions here. 1 over, let me say, integrate both sides. Then what do we get? Integral dv over 1 minus v squared equals integral dx. So that means integral 1 over 1 minus v minus 1 over 1 plus v dv equals integral dx. And then you can say that ln, absolute value. So this part, I use partial fractions. We know that from math 114, to integrate a function of this form, we can use partial fractions. 1 minus v squared can be written as 1 minus v times 1 plus v. So I can write this one as a over 1 minus v plus b over 1 plus v. And then we can find a and b. But because it's a very simple case, simple calculations, I just did that by guessing, basically. That the first coefficient must be 1 and second coefficient must be -1, because in that case, when you get common denominator, Denominator will be 1 minus v squared, and numerator will be 1 plus v minus bracket 1 minus v. Sorry, it will be plus here, because 1 minus v, 1 plus v plus 1 minus v, it will be 2 in the numerator. And then I also need an extra factor of 1 over 2 here, so that I'll get 1 over 1 minus v squared. Right? See, right here, 1 over 1 minus v plus 1 over 1 plus v. This is 1 plus v plus 1 minus v over 1 minus v squared, and that's 2 over 1 minus v squared. And then when I multiply with 1 over 2, I'll get 1 over 1 minus v squared. But if you are not comfortable with this method and you prefer writing as a over 1 minus v plus b over 1 plus v, please do that. And then you can find a and b, of course. And you will see that a and b will be basically 1/2 each of them. Because basically a here is 1/2 times 1, which is 1/2, and b is 1/2 times 1, which is also 1/2. Now, what is the integral 1 over 1 minus v? It's going to be ln, absolute value 1 minus v. Do we need extra minus sign in front? Because when I differentiate this, it's going to be minus 1 over 1 minus v, but this is 1, so I need the extra minus in front. So 1/2 times minus this, and antiderivative of 1 over 1 plus v is ln 1 plus v. And then integral dx, which is going to be x plus c. And then I can write this one as 1/2 ln absolute value 1 plus v divided by 1 minus v equals x plus c. And that means ln absolute value 1 plus v divided by 1 minus v equals 2x plus, we call it d, 2c, which I can call it d. D is 2c. And then we need to find v here. So 1 plus v divided by 1 minus v will be e to power 2x plus d, which is going to be e to power d times e to power 2x. And so this one in absolute value is equal to this. And then I can say 1 plus v divided by 1 minus v equals plus minus e to d times e to the 2x. Right? See, ln of something is, ln of some expression is 2x plus d. That means that expression will be e to power 2x plus d, which can be written as e to power d times e to power 2x. And now this is absolute value of this guy is equal to this expression. So this guy here will be plus minus this expression. And then plus minus e to power d, I can call it f. Then I'll have f e to power 2x. And then if I cross multiply, 1 plus v equals 1 minus v times f e to power 2x. And that means 1 plus v equals f e to power 2x minus v f e to power 2x. Then v, if I factor v out, times 1 plus f e to power 2x equals f e to power 2x minus 1. And then v will be equal to f e to the power 2x minus 1 divided by 1 plus f e to the power 2x. So this is the solution for v in this case. And then we want to find y. Remember, our final goal is to find y. Next, to find y, we have to use the fact that v is x minus y plus 1. So y will be x plus 1 minus v, and that's going to be x plus 1 minus this expression here, f e to the power 2x minus 1, f e to the power 2x plus 1. And we can write this one as x plus 1 plus 1 minus f e to the power 2x divided by 1 plus f e to the power 2x. Minus this bracket will be 1 minus f e to the power 2x. And denominator, I rewrote it again. So this is the final answer for y in case 2. So we have a parameter here, f, which we can leave it as f because the initial condition was not given. If the initial condition was given, we had the first order differential equation with one initial condition, we would have a unique solution. But without the initial condition, we naturally have a parameter that we have to leave it as it is. So here f is a positive or negative constant. Because f was plus minus e to the d. E to the d was a positive constant. F is plus minus that. So f is a positive or negative constant. So this is the final answer for y in case 2. And in case 1, we had two solutions, y equals x and y equals x plus 2. Y equals x and y equals x plus 2 in case 1, and y equals this function in case 2. All right, now let's look at another type of equation, which again can be solved using substitution. It's called Bernoulli equation. Bernoulli so this is an application of substitution. We are still in the topic of substitution. So the general form of a Bernoulli equation is an equation of the form y prime plus p of x times y equals q of x times y to power n. And n here is a non-negative integer, where n is a non-negative integer. Non-negative integer means either 0 or 1 or 2 and so on. Now, let's consider different possibilities for n. So case 1, we're saying n is a non-negative integer, so n could be 0 or 1 or bigger than 1. So based on that, we want to consider different cases. Case 1, if n equals 0, then what do we have? Then we'll have y prime plus p of x times y equals q of x. Q of x times y to power 0, which is same as q of x. So this is a linear first order ODE, which was covered before. Remember, we already covered linear first order ODE. And we saw how to solve this type of equation. We had to use integrating factor, if you remember. So let me not repeat all those steps. We already know how to do it. So case 2, if n equals 1, then we'll have y prime plus p of x times y equals q of x times y, right? N is 1, so right-hand side becomes q of x times y. And I can write this one as y prime equals, let me take this term to the other side. Then what do we get? Y prime equals q of x times y minus p of x times y. And this is q of x minus p of x times y. And that means, what type of equation is this? Y prime equals q of x minus p of x times y. So this is a separable equation. Separable equation because, we can separate all y's into one side, all x's into the other side. We just need to divide both sides by y if it's, of course, non-zero. Again, so if you want to solve this, you have to consider two possibilities. If y is constant function 0, and second possibility, if y is not constant function 0, then you can divide both sides by y, and then you can write it as, dy over y equals, p of x minus q of x dx, and then you can integrate both sides. Sorry, q of x minus p of x dx, q of x minus p of x dx, and then we can integrate both sides and solve for y. So this case is separable, and we already covered it. You can fill in the details. And then case 3, if n is bigger than 1, then use the substitution v equals y to power 1 minus n. To convert the equation, the Bernoulli equation, into a linear first order ODE. So if n is 0, it's already linear first order. If n equals 1, separable. If n is bigger than 1, use the substitution v equals y to power 1 minus n to convert it into linear first order. How did we come up with this type of substitution v equals y to power 1 minus n? Well, it's hard to guess. It's hard to guess, and for this reason, I want you to just simply remember that if you have a Bernoulli equation, an equation of this type, y prime plus p of x times y equals q of x times y to power n, and if n is bigger than 1, then you have to remember the type of substitution we need. The type of substitution we need is v equals y to power 1 minus n. Please remember it because it's hard to guess or it's hard to come up with it during the exam. So please just remember that we have to use this type of substitution, v equals y to power 1 minus n, in order to convert it into a linear first order ODE. All right, let's look at this example. Solve xy prime plus y times x plus 1 plus x times y to power 5 equals 0 with y of 1 equals 1. So first we can write it as a Bernoulli equation. If you look at the general form of a Bernoulli equation, we can see that we can write it as a Bernoulli equation. We just need to take this term to the other side. So first Note that the equation above is a Bernoulli equation xy prime plus x plus 1 times y equals minus x times y to power 5. And then I can divide both sides by x. Then I get y prime plus x plus 1 over x times y equals minus y to power 5, because the general form was this: y prime plus p of x times y equals q of x times y to power q of x times y to power n. So basically we can say here the Bernoulli equation, and our functions here are p of x, which is x plus 1 over x, and q of x is minus 1, and n is 5. So let's use, because n is 5, since n equals 5, which is bigger than 1, we use the substitution. The substitution, v equals y to power 1 minus n, which is y to power 1 minus 5, and that's y to power minus 4. And then now we can rewrite everything in terms of v. Now we need to rewrite this equation that we had. So let me call this one equation, maybe star. Rewrite equation star above in terms of v. All y's must be replaced with v's. See, when you use a substitution and you want to substitute y with v, then you cannot have y and v, both of them appeared in your equation. Similar thing happened in integrals. If integrals you wanted to, let's say, change from t to s, then your integral cannot contain both t and s. It must contain only one of them. If you want to convert from t to s, then all t's must be replaced with s. And they have to be written in terms of s. When I say must be replaced, I don't mean just change t to s, because t is probably not equal to s, but I mean you have to write them in terms of s. So I mean no t's at the end, no t's is allowed to be appeared, and they have to be all replaced, and they must be written in terms of s. So similar thing here, if you want to go from y to v, then we cannot have some y's and some v's in our equation. All y's must be written in terms of v, and similarly y prime must be replaced in terms of v prime, must be written in terms of v prime. And at the end, I'm only allowed to have v and x, no y anymore. All right, now what will be, let's first see what will be v prime. So to do that, let's first find v prime. V prime will be derivative of y to power minus 4 according to the power rule. Power rule, we can write this one as minus 4 times y prime times y to power minus 5. So that means y prime will be equal to, because you see in my equation star, I have y prime. Y prime will be v prime over minus 4 times y to power 5. From this equation, I can easily find y prime. Y prime will be prime over minus 4 times y to power 5. So substitute back. If I substitute back, then I'll have minus 1 over 4 v prime times y to power 5 plus x plus 1 over x times y equals minus y to power 5. Now, if I divide everything by y to power 5, assuming is non-zero, well, which is non-zero because y of 1 was given as 1. So that means y cannot be constant function 0 because constant function 0 would be always 0. But we know that y at some point, it's 1. So I can say that instead of assuming, it's not an assumption. Basically, it's a fact that y is not 0 because according to the initial condition, y of 1 is 1. So y cannot be constant function 0. So maybe I can say that note y is not 0 since y of 1 is 1. So let's divide. So we can divide by y to power 5. Then I'll have minus 1 over 4 v prime plus x plus 1 over x times y to power minus 4. Right? Y divided by y to power 5 will be y to power minus 4. And right-hand side becomes minus 1. Now, y to power minus 4 is v. Remember, v was y to power minus 4. So v is y to power minus 4. Then I'll have minus v prime over 4 plus x plus 1 over x times v equals minus 1. Now, if I multiply everything by minus 4, then I'll have v prime minus 4 times x plus 1 over x times v equals 4. So this is a linear first order ODE. Remember, v prime plus p of x times v equals f of x. So this is a linear first order ODE. Our independent variable right now is x and our unknown function is v. We have to solve for v. How did we solve this type of equation? Using integrating factor. We need to solve this ODE using the integrating factor. What will be the integrating factor R of x? R of x will be e to power integral p of x dx. And p of x here is integral minus 4 times x plus 1 over x dx. And what will be this integral here? I can take minus 4 out. E to power minus 4 times integral 1 plus 1 over x dx. And then this is e to power minus 4 times x plus ln x, or ln absolute value x. And then I can write this one as e to power minus 4x minus 4 ln absolute value x. And then I can write this as e to power minus 4x times e to power ln absolute value x to power minus 4, right? E to power minus 4x minus this. So I can write e to power minus 4x times e to power minus 4 ln absolute value x. E to power minus 4 ln absolute value x, I can write it as e to power ln absolute value x, the whole thing raised to power minus 4. And then This can be written as e to power minus 4x times absolute value x to power minus 4. Because we know that e to power ln t is always t. E to power ln t is t, so e to power ln absolute value x is x. E to power ln absolute value x is absolute value x. So it seems my screen is freezed. E to power ln absolute value x is absolute value x. So this is going to be e to power minus 4x times absolute value x raised to power minus 4 raised to power minus 4 is from here. I rewrote it again. Okay, now I want you to notice that we are looking for a solution around x equals 1. Remember the initial condition was at 1, y of 1 equals 1. And remember that we said that for the solution of differential equation exists and is unique locally around the point x0 that is given. So basically our goal is to find a solution around this point. Now, if that solution is defined globally on minus infinity to infinity, well, then that would be great. But otherwise, still is okay, right? So we can assume that x is positive because x is supposed to be around 1. Around 1, we need to have a unique solution. We want to find that solution. And we assume x is positive for now, and we find a solution. If that solution is defined globally, that would be great, but otherwise still is okay. So let's assume x is positive. So I can say that assume x is positive since it is around x0 equals 1. And then absolute value x will be same as x. If x is positive, absolute value x will be same as x. So I will have e to power minus 4x times x to power minus 4. So this is the formula for r of x. Now, what was the equation? The next step. Remember, we did this, we have done this several times. That after we find the integrating factors, we can write the left-hand side as d to dx of r of x times v. Previously we said y, but here instead of y we have v. And right-hand side would be r of x times f of x. And f of x in this case is 4. Look at here, f of x is 4. Right-hand side is 4. So this is 4 times r of x. So integrate both sides now. If we integrate both sides, then we get r of x times v equals integral 4 times r of x, which is integral r of x is this guy here, 4 times e to power minus 4x, x to power minus 4 dx, e to power minus 4x, x to power minus 4 dx. And this indefinite integral cannot be computed, because for finding this indefinite integral, we need antiderivative of e to power minus 4x times x to power minus 4. It can be shown that this function has no antiderivative, so we cannot write it as a closed form. So it cannot be written in a closed form, since e to power minus 4x times x to power minus 4 has no antiderivative. See, if this was x to power 4, then that would have been easy, because x to power 4 times e to power minus 4x, the antiderivative for that function can be easily found using integration by parts. But this is x to power minus 4, not x to power 4. So instead, cannot be written in closed form. So instead, we can write it as an area function. Area function. So we can write this one as r of x times v equals integral 1 to x for e to power minus 4x minus 4t t to power minus 4 dt. See, we are looking for antiderivative of this function, right? Well, this is an antiderivative for this function, because we know that from math 114, we know that the area function, which you denoted with capital F or capital A in math 114, capital F of x or capital A of x, is an antiderivative for small f. You know that if you define capital F of x, see, this is what you saw in math 114, that if you define capital F of x as integral 1 to x f of t dt, then capital F prime of x will be small f of x. So this is called area function. Sometimes you can also denote it with capital A of x. So in any case, this will be antiderivative for your function, because if you differentiate this function, as long as this function is small f is continuous, this function capital F will be differentiable, and capital F prime is small f. So we are looking for antiderivative for our function. We cannot write it as closed form because this function has no antiderivative, but area function is always an antiderivative as long as small f is continuous. Well, small f here is continuous on 0 to infinity, because I cannot, it's not continuous on minus infinity to infinity because of this negative power. Basically, this is 1 over x to power 4, which is discontinuous at 0. But on 0 to infinity, this is continuous, and therefore area function can be used as an antiderivative. So we can write it as an area function. Maybe I can say that from math 114. We know that area function, let me write it this way. Capital F of x equals integral a to x f of t dt is antiderivative of f of t if f of t is continuous. So I can write this as, let me write it again. So r of x times v equals integral 1. I'm choosing my a to be 1 because x0, the initial condition, was given at 1. 1 to x for e to power minus 4t, t to power minus 4 dt for x in 0 to infinity. Why 0 to infinity? Because this is the interval at which e to power minus 4t times t to power minus 4 is continuous. Open interval 0 to infinity. this function is continuous. So v will be equal to well, we can include some constant c as well. Let me say plus c here. You can always add a constant c because derivative of constant function is 0. So if this is an antiderivative for this function, if I add it with the constant, still it will be an antiderivative for my function. So v of x will be equal to 1 over r of x times integral 1 to x, 4 times e to power minus 4t, t to power minus 4 dt, plus c over r of x. I'm dividing everything by r of x. Now I want v of 1 to be, so I know y of 1. I know what y of 1 is. Remember in the original question, y of 1 is given as 1. So what should be v of 1? First, let's find y of x. What is y of x? If you remember, v was y to power minus 4. So y will be v to power minus 1 over 4. V to power minus 1 over 4. So y will be equal to, I already have the formula for v, 1 over r of x, integral 1 to x, 4 e to power minus 4t, t to power minus 4, dt plus c over r of x, and then the whole raised to power minus 4. The whole raised to power minus 1 over 4. And then we need to just find c. To find c, use the initial condition. What was the initial condition? Y of 1 equals 1. Y at 1 must be 1. Okay, now let's replace x with 1. So y of 1 is equal to 1 over r of 1. Integral 1 to 1. Integral 1 to 1 of any function is 0. So we have no problem there. Plus c over r of 1 to power minus 1 over 4. This is supposed to be 1. Now this guy here is 0 because integral 1 to 1 is always 0. So then I'll have y of 1 equals c over r of 1 to power minus 1 over 4 equals 1. So that means c over r of 1 must be 1, because if I raise both sides to power minus 4, 1 to power minus 4 is also 1. And that means c is equal to r of 1. R of x, if you remember, r of x was this guy, x to power minus 4 times e to power minus 4x. E to power minus 4x, x to power minus 4. So this is going to be e to power minus 4. So c is e to power minus 4, substitute back. And then y will be equal to 1 over r of x, 1 over r of x, integral 1 to x, 4e to power minus 4t, t to power minus 4, dt plus c over r of x to power minus 1 over 4. C is e to power minus 4. E to power minus 4 over r of x, the whole thing to power minus 1 over 4. This is the final answer. Okay, guys, so what you need to remember for the exam is that if you have Bernoulli equation for n bigger than 1, you have to use the substitution v equals y to power 1 minus n. Then we had a linear first order equation, and we had to follow the steps for solving a linear first order ODE. We just had a small problem in the middle that we encountered a function that had no antiderivative in a closed form. But still that was okay, because instead of using a closed form, we could use an area function. The area function is also an antiderivative. So instead of writing as closed form, we wrote as area function. Still that's okay. Now this area function is a function of x, and r of x is a function of x. So this whole expression, the right-hand side, is a function of x. So we wrote basically y as a function of x, which is what we were supposed to do. Of course, if so antiderivative is always, area function is always antiderivative. But if the function has antiderivative, well, you have to write it in a closed form in the exam. So basically, even if this function was, let's say, e to power minus 4t only, and you wrote it this form, then this would be still correct, but it's not as simplified as possible, because then e to power minus 4t has an antiderivative, and we could simplify it further. So this writing the antiderivative as an area function is always valid, but if the function has antiderivative, then you can simplify it further and write it as a closed form. And that's what you have to do in the exam, that if it has antiderivative, write it in a closed form. If not, just leave it as an area function. Okay, guys, so that's all for today. And we covered substitution, and one other type of substitution for a specific type of equation was left. We couldn't finish it today, and I'll tell you about it next time. Okay, guys, so thank you and see you next time.